imagine two objects, each cramming more mass than our sun into a sphere the size of a city, spiraling toward each other at a significant fraction of light speed. When they collide, they unleash more energy in a single second than our sun will produce in its entire 10 billion year lifetime. This isn't science fiction. This is what happens when neutron stars merge. And it's one of the most spectacular events in our universe. Neutron stars are the collapsed cores of massive stars that exploded as supernovas. They're so incredibly dense that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. That's roughly the weight of Mount Everest compressed into something you could hold in your hand, if physics would allow it. These stellar remnants pack between 1.4 and 2 times the mass of our sun into a sphere just 12 to 15 miles across. To put that in perspective, if Earth were compressed to the same density, it would fit inside a baseball stadium. The surface gravity on a neutron star is mind-boggling. It's about 2 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, you'd be instantly flattened into a layer of atoms, just a fraction of a millimeter thick. The escape velocity from these objects is roughly half the speed of light, meaning you'd need to travel at 150,000 kilometers per second just to leave the surface. Now, when two of these cosmic monsters end up in orbit around each other, something extraordinary begins. These binary neutron star systems slowly spiral inward over millions or even billions of years. As they orbit, they lose energy by radiating gravitational waves, ripples in the fabric of spacetime itself that travel outward at the speed of light. Einstein predicted these waves over a century ago, but we only detected them directly for the first time in 2015. As the neutron stars draw closer together, their orbital speed increases dramatically in the final moments before collision. They're whipping around each other hundreds of times per second. The gravitational waves they emit become stronger and more frequent, creating what scientists call a chirp signal. The frequency rises higher and higher until the stars finally merge in a cataclysmic collision. What happens next depends on the combined mass of the two neutron stars. If their total mass is below a certain threshold, they merge to form a larger, more massive neutron star. This new object is incredibly hot and violently spinning, sometimes rotating hundreds of times per second. If the combined mass exceeds about 2.5 to 3 solar masses, even the incredible pressure inside a neutron star can't support the weight, and the merged object collapses into a black hole. But here's where things get really interesting. The collision doesn't just produce gravitational waves. It also triggers what astronomers call a kilonova, an explosion that's roughly 1,000 times brighter than a typical nova. During the merger, intense tidal forces rip material off the neutron stars and fling it into space. This ejected matter, enriched with neutrons, becomes a cosmic forge for creating heavy elements. You see, most of the lighter elements in the universe, like hydrogen and helium, were created in the Big Bang. Elements up to iron are forged inside stars through nuclear fusion, but elements heavier than iron, like gold, platinum, uranium, and thorium, require extreme conditions that even stellar cores can't provide. For decades, scientists debated where these heavy elements came from. Neutron star mergers provided the answer. The neutron-rich material ejected during these collisions undergoes rapid neutron capture, a process called the R process. Atomic nuclei absorb neutrons faster than they can decay, building up heavier and heavier elements in seconds. This process creates roughly half of all elements heavier than iron in the periodic table. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, they all came from neutron star mergers billions of years ago. On August 17th, 2017, humanity witnessed one of these cosmic spectacles for the first time across multiple wavelengths. The LIGO and Virgo gravitational wave detectors picked up the signal from two neutron stars merging in a galaxy 130 million light years away. Just 2 seconds later, NASA's Fermi Space Telescope detected a gamma ray burst from the same location. Within hours, telescopes around the world and in space turned toward the source. What they saw was unprecedented. Astronomers observed the kilonova's light across the entire electromagnetic spectrum, from gamma rays to radio waves. They watched as the explosion's color changed from blue to red over several days, exactly as theoretical models had predicted. The blue light came from lighter elements moving at high speeds, while the red light indicated the presence of heavy elements like gold and platinum. Scientists estimate that this single merger produced about 10 times the mass of Earth in pure gold. It also created roughly 3 to 5 Earth masses of platinum and similar amounts of other precious heavy elements. Every atom of gold ever mined on Earth, roughly 200,000 tons. could have come from just one or two neutron star mergers in our galaxy's ancient past. The 2017 detection opened a new era in astronomy called multi-messenger astronomy. For the first time, scientists could study the same cosmic event using both gravitational waves and electromagnetic radiation. This combination provides far more information than either method alone. It's like the difference between listening to a concert and actually attending it in person. Since that groundbreaking observation, gravitational wave detectors have identified several more neutron star merger candidates. Each detection helps refine our understanding of these extreme events. Scientists are learning about the equation of state of neutron star matter, essentially how this ultra-dense material behaves under extreme pressure. This research probes physics at densities we can never recreate on Earth. Current research focuses on understanding exactly how much material gets ejected during mergers and how efficiently it produces heavy elements. Scientists are also investigating whether neutron star mergers are the primary source of all heavy elements, or if other events contribute significantly. Some evidence suggests that mergers between neutron stars and black holes might also create heavy elements, though we've only recently begun detecting these hybrid collisions. Future gravitational wave detectors, like the planned Einstein telescope and Cosmic Explorer, will be far more sensitive than current instruments. They'll detect neutron star mergers from across the entire observable universe, potentially thousands of events per year. This wealth of data will revolutionize our understanding of these cosmic collisions and the extreme physics governing them. The next time you look at a piece of gold jewelry or hold a platinum ring, remember that you're touching stardust forged in one of the universe's most violent events. Those atoms survived a journey lasting billions of years, traveling through space until gravity gathered them into our solar system. Neutron star mergers remind us that we're intimately connected to the cosmos, the universe's most extreme phenomena, created the very elements that make up our technology, our planet, and even our bodies. What other cosmic secrets are waiting to be discovered in the collisions of these stellar remnants?